positive x-axis. So for example, the point 6, 2, x equals 6, y equals 2, would be located by radiating out a distance of 2 times the square root of 10 from the origin, having rotated 18.43 degrees counterclockwise from the positive x-axis. It doesn't matter if you list your angle in degrees or radians as long as you know what unit you have. So 18.43 degrees could also be listed as 0.3217 radians. In this section, we will be looking at how to read equations in polar coordinates to determine what kind of graph. So for example, let's say you have r equals 5. That means your radius is always 5. And you assume the center again is the origin 0, 0. So if the radius is always 5 coming out from the origin, that's going to give us a circle of radius 5 centered at the origin. That's actually the definition of a circle. It's the set of points all the same distance from a fixed center. Remember from our section about how to obtain polar coordinates, the radius is the hypotenuse of a right triangle where x and y are the legs of the right triangle. So the radius is always equal to the square root of x squared plus y squared. So if I rewrote this equation into rectangular coordinates just means the regular x and y system, then r equals 5 in rectangular coordinates is equivalent to the equation the square root of x squared plus y squared equals 5. You could square both sides of that and get x squared plus y squared equals 25, and that is the typical equation of a circle centered at the origin with radius 5. What if instead of r equals a number, you had theta equals a number? What would that mean? For example, what if we had theta equals 3 pi over 4? Well, that would mean that the angle stays 3 pi over 4, and the radius could be anything. It could be a short number, it could be a long number. If you thought about putting those two pieces of information together, you would get a line tilted at the angle 3 pi over 4. Now, I know that I have the angle drawn from the origin into quadrant 2 at an angle of 3 pi over 4. I also have the other part of the line down in quadrant 4, so you may be wondering, well, wait a minute, that's not 3 pi over 4. That angle would be 7 pi over 4. Well, radii can be labeled as negative, and if you have a negative radius, it means that you've done a 180-degree flip from the normal direction. So if the radius is positive, then those will create points going up into quadrant 2 at an angle of 3 pi over 4 from the positive x-axis. If the radius is negative, then you'll do a 180-degree flip from that, and you will get the other half of the line down in quadrant 4. In terms of converting to rectangular coordinates, remember that tangent is equal to y over x, and in this case, tangent of 3 pi over 4 is -1, and so you could take that information, -1 equals y over x, and you get the linear equation -x equals y, or a line with a slope of -1 going through the origin. Just like with graphing in rectangular coordinates, it helps to make a table when graphing in polar coordinates. What you're doing is you are replacing theta or r and figuring out what the other one has to be. In this case, with r equals 4 plus 3 cosine theta, it's probably easier to plug values in for theta and then calculate what you would get for r. I'm going to work in radians in this case, so if I put 0 in for theta, cosine of 0 is 1, and so 4 plus 3 times 1 is 7, so the radius would be 7. If you plug in pi over 3, cosine at pi over 3 is 1/2, so 4 plus 3 times 1/2 is 4 plus 1/2, or 5/2, so the radius would be 5/2. If I plug in pi over 2, cosine of pi over 2 is 0. You're at the top of the unit circle. So 4 plus 3 times 0 is 4. So the radius is 4. If I plug in 5 pi over 6, cosine at 5 pi over 6 is negative square root of 3 over 2. So multiplying that by 3 and adding it to 4 gives you approximately 1.4019 as your radius. If I plug in pi, cosine of pi is negative 1. 4 plus 3 times negative 1 would be 4 minus 3, or positive 1. So the radius is 1 when the angle is pi, etc. So, you can see kind of what we're doing here. Once you get enough of these points, just like with graphing in rectangular coordinates, you can then start to sketch the graph. So now that we built our table, we can plot these points. When you're plotting in polar coordinates, you first want to think about the angle. So 0 radians means you have not rotated and you're on the positive x-axis. So there's a point at a radius of 7 from the origin on what looks like the x-axis. If I rotate to pi over 3, again 60 degrees is pi over 3, my radius is 5.5. So notice there's a point 5.5 units out from the origin. Pi over 2 is 90 degrees, so I'm on what looks like the y-axis, and the radius is 4. There's a point 4 units out from the origin when I've rotated 90 degrees, or pi over 2. At 5 pi over 6, or 150 degrees, the radius should be shorter, 1.4, so notice there's a point about 1.5 out from the origin at 150 degrees, or 5 pi over 6. At pi, we're on the negative side of the x-axis, and the radius should be 1. At 5 pi over 4, I'm in quadrant 3, and the radius should be 1.87, so almost 2. You can see a point there that's almost 2. And then at 4 pi over 3, the radius should be 2.5. So at an angle of 240 degrees, or 4 pi over 3, I've radiated out 2.5 spaces. And at 3 pi over 2, or 270 degrees, I'm down the negative part of the y-axis, and the radius should be 4, similar to it, where it was at 90 degrees, etc. So if you get enough of these points, you can connect them and get your graph. Now, some of the graphs do have special names. This one is called a cardioid because it kind of looks like a heart. You get cardioids with equations of this form, where you have a number for a constant added to a coefficient times cosine or sine. You could also have sine. If you did have sine, there'd be a 90-degree rotation of the shape from what we have. I'm not going to focus a whole lot on the names, but you should be aware that some of the forms have special names. Once again, just like with all graphing, making a table to help you plot points is helpful. I know that we have graphing calculators and Desmos that will help us graph these graphs quickly. That obviously is very helpful, but actually plugging the numbers in and thinking about where the points are coming from is kind of fundamental in you understanding the equations and things you might want to do with them, later in later courses of mathematics. So here we're plugging in different angles. Again, I'm working in radians, and we have the equation r equals 7 times sine of 3 theta. Notice the 3 times theta is going to kind of speed things up. So when I plug in 0, sine of 0 is 0, so the radius would be 0, so my graph will start on the origin actually. And notice I'm plugging in a fairly small angle, pi over 12, but by the time I multiply pi over 12 by 3, it's equivalent to pi over 4. Sine of pi over 4 is 1 over the square root of 2, so multiply that by 7, and you get 7 over the square root of 2. You can estimate what that value is. That value is approximately 4.94, so a little bit less than 5. If I plug in pi over 6, 3 times pi over 6 would be equivalent to pi over 2. Sine is 1 at pi over 2, so 7 times 1 is 7, so my radius is 7 when I plug in pi over 6. When I plug in pi over 2, I get sine of 3 times pi over 2, which is negative 1, and so the radius is negative 1 when I plug in the angle pi over 2. When I plug in 5 pi over 6, or 150 degrees, that is equivalent to sine of 15 pi over 6 or 5 pi over 2. So I've already rotated back around to the top of the circle and my radius is 7. So the 3 in with the theta is kind of speeding up the points, and we're getting quicker rotations, and we'll see that in the graph. So here is the graph of r equals 7 times sine of 3 theta, and notice I have 3 loops. I've rotated a full rotation 3 times because of the 3 times theta. And this is called a rose. It's a 3-petaled rose is the name of this type of graph. And again, it probably would be helpful to actually plot even more points than the ones I have if you were really trying to draw this by hand and not have some software draw it for you. But you could see the points that we do have in the chart showing up on the graph. So again, the 3 speeds up the frequency to 3 times, and so I'm getting 3 complete loops from 0 to 2 pi, and that gives me 3 petals on this flower. As in our other examples, making a table is going to help us graph. So we have here r equals 6 times sine of theta, so 0 is going to give us 0 because sine is 0 at 0. When I plug in pi over 6, sine's 1/2, so 6 times 1/2 is 3. When I plug in pi over 3, sine is the square root of 3 over 2. So multiply the square root of 3 over 2 by 6, and I get 3 times the square root of 3. At pi over 2, sine is 1, and so 6 times 1 is 6, so that gives me my highest radius of 6. At 5 pi over 6, sine is 1/2. 6 times 1/2 is 3. At 5 pi over 4 down in quadrant 3, sine is equal to -1 over the square root of 2. So multiplying that by 6 gives us -6 over the square root of 2, which is approximately -4.24. And 3 pi over 2 is at the bottom of the circle, sine's equal to -1, so 6 times -1 is -6. And by the time I rotate back to 2 pi, sine is 0 again, and I will be back to the origin. The graph then of r equals 6 times sine theta is actually a circle, not centered at the origin, but instead centered at 0, 3. Notice that my highest radius value is 6, and you can see that at the top of this circle, and then the other values kind of round out the circle. I have 1 loop, so you could put this in the category of the rose graphs, but you only have 1 petal, and that's because it's 6 times sine of 1 times theta. In that last graph, we had 3 times theta, so there were 3 petals. Here, there's only 1 petal. You would also get a circle if you had r equals 6 times cosine theta, but that circle would be rotated 90 degrees so that the top of the circle would now be down the positive x-axis, because remember, cosine gives you the x-coordinates, and so the end effect is you get this same circle, but it would be stretched out down the positive x-axis. You could always rewrite polar equations in terms of rectangular coordinates. You do so by just replacing how the two are defined between the different systems. Remember, the radius is the hypotenuse of the right triangle formed with x and y as the legs. So r is always replaced with the square root of x squared plus y squared. And 4 would just stay the number 4. Remember from right triangle trig that r times cosine theta will always give you your x coordinate when you're going back and forth between polar and rectangular coordinates. So that means that x divided by r is equivalent to cosine of theta. So 3 times cosine theta is equivalent to 3 times x over the square root of x squared plus y squared, because r is the square root of x squared plus y squared. I put a plus or minus in front of the square root because, you know, to get this full graph, you actually are going to have to split this up into 2 different functions. I mean, as it is, it doesn't fit the definition of a function where, you know, there's only one y for each x. But you'd put 2 functions together to get the full graph. So one one of the functions would be treating that radius as positive and the other would be treating the radius as negative, and then you would get the full graph. You also could manipulate this, like I could multiply both sides by the denominator square root of x squared plus y squared and write it in different forms. As long as they're equivalent, it would be fine. Here's another example where we are rewriting a polar equation in rectangular coordinates. And here I dig a little deeper into how you can write the equation in different forms. So I start off with r being the square root of x squared plus y squared, and then 6 is 6. Sine is equal to y divided by r, because r times sine of theta always gives you your y coordinate. So rewriting that, sine of theta is equivalent to y over the square root of x squared plus y squared. Now with that equation, again, you could put plus and minus in order to get, the two different sides. You would have to split this up into two separate functions to graph them together if you actually were working with functions in rectangular coordinates. If I multiplied both sides by that denominator of the square root of x squared plus y squared, then the square root times the square root gives us just x squared plus y squared to the first power, and I'm left with the numerator of 6y. You could leave the equation in that form. Again, it looks a little more cleaned up, certainly, than our first form. That is a circle. Remember, we talked about this graph as a circle. If you subtract the 6y from both sides and then complete the square, you end up with the more standard equation of the circle, x squared plus y minus 3 squared equals 9. So the center is 0, 3, and the radius of the circle is 3. So if you were back in college algebra class studying equations of circles, you would recognize that as the standard equation of a circle whose center is at 0, 3, and whose radius is 9. I know we work with sine, cosine, and tangent a lot more than secant and cosecant and cotangent, but they still have their place. For example, in polar coordinates, if you take the equation r equals 4 times cosecant of theta and rewrite it in terms of rectangular, the r becomes the square root of x squared plus y squared, and 4 times cosecant is the same as 4 divided by sine of theta. So if I then rewrite sine of theta as y over r, remembering that r is the square root of x squared plus y squared, and then we clean that up a little bit, so dividing by anything is the same as multiplying by its reciprocal, so I flip the y over the square root of x squared plus y squared around, and I then get the square root of x squared plus y squared equals the square root of x squared plus y squared times 4 over y. I could divide both sides now by the square root of x squared plus y squared, and they cancel out. That gives me 1, because when I divide both sides by the square root, I actually get 1 on the left side. So 1 equals 4 over y is the same as 1 times y equals 4. So r equals 4 cosecant theta ends up just being the horizontal line y equals 4. It's equivalent to a horizontal line y equals 4. You'd get a similar situation if you had r equals 4 times secant theta. You would get a line, but it would be a vertical line at x equals 4. Don't let equations in different forms throw you off. For example, if you had r squared equals cosine of 2 theta, you still would want to build a chart to help you plot points, but this time instead of plugging in values for theta, instead consider values for the radius. For example, let's say the radius is 1. Then plugging 1 into the formula, 1 squared is 1, and you have the new equation 1 equals cosine of 2 theta. You can then solve these equations like we learned in the previous chapters of trigonometry. I use inverse cosine in this case. With cosine equal to 1, I don't really formally need to do it. I just know that cosine is 1 at 0 and 2 pi and 4 pi. So solving that for 2 times theta, I would get the collection of possible angles, 0, pi, 2 pi, for example. If I had a radius of 3/4, and I plug that into the equation, I would get 3/4 squared, or 9/16, is equal to cosine of 2 theta. Solving that equation for theta, I would use inverse cosine of 9/16, and that would be equal to 2 theta. Solving for theta would give me 0.4867 and 2.6548, but remember that cosine and sine are periodic functions that repeat over and over again, and in this case the wavelength would be pi, so I would continue to get other angles by adding n times pi to these two solutions. The other two possible values that I put in the chart is 1/2 for r and 1/4 for r. You could solve similar equations and notice you get multiple possible angles, and that ends up giving us a kind of loop-de-loop graph that looks kind of like an infinity sign, and we will see that in the next screen. Shown is the graph of the Lemnos gate. That's the name of the graph that's created by r squared equals cosine of 2 theta and other graphs of that form. I have various points drawn that correspond to the radii and the angles that give us those radii in our chart. I don't necessarily have all those points plotted, but several of them. When you're working with polar coordinates and polar equations, remember that the radius is the hypotenuse of the right triangle, where x and y are the legs of the right triangle. So r is always equal to the square root of x squared plus y squared. X can always be computed as r times cosine theta, and y can always be computed as r times sine theta. And that'll allow you to go back and forth between polar equations and rectangular equations.